Okay, so for our next class, we want to talk about vectors. So we will use arrows to represent vectors, and this end is called the tail, and this end is called the head. Now we will use diagrams to represent vectors, and it's pretty easy. We want to draw these roughly to scale. We don't need to be that precise. I mean, I've got a ruler here, but that's maybe a bit of overkill. But it's good to draw it roughly to scale. Okay, so how do we draw this acceleration vector? 40 degrees west of north. Well, first notice that west of north means towards the west, starting from the north. So towards the west, starting from the north, will be over here, and we want to do that as 40 degrees. Okay, so we drag that fancy protractor over. It's now at 40 degrees, and then we can just draw the vector, 3 meters per second squared. And so there we have it, our acceleration vector, 40 degrees towards the west, starting from the north. So on the next page, example 3, there's 4 vectors for you to draw on a single coordinate system. Pause the video and draw those now. Okay, so this is what it should look like. First one, 40 degrees towards the east, starting from the north. 20 newtons long, that's a force vector. Here's one 10 degrees south of east. 5 meters per second, that's a velocity vector. 15 meters southwest means exactly 45 degrees. And then 20 degrees towards the north, starting from the west. That's how we'll draw that acceleration vector there. Okay, so now we can draw vectors, and that means we can start to do math with them. The first and easiest math is to scale a vector. So if this vector is v, let's draw all these other ones. Well, 2v is just going to be the same direction and twice as long. So that vector will be twice v. Half of v will just be same direction, half as long. Negative v will be the same length, but just pointing the opposite way. And negative 2v, it's the opposite way and twice as long. So that's how we can multiply vectors by a scalar. Oh, sorry, that's just negative v. And this is negative 2v. Okay, so now we can multiply vectors by a number. The next mathematical operation we want to do is addition. And addition is fairly algorithmic, all right? Here's how to go about adding vectors. So if you want to add 2 vectors together, just draw the first one using the techniques that we've just discussed. Then starting at the end of the first one, draw the second one. So I'm just making up 2 vectors. There's the second one at the end of the first one. And then the sum, or what we're looking for when we're adding 2 vectors, the resultant as it's sometimes called, just goes from where you started to where you end up. So this would be the sum of those 2 blue vectors. Let's try a quick example. So this is a graphical technique. Here I've kind of got it built here already. So we'll pull those out of the way. And so here's the example, the 2 vectors we want to add, 3 meters northeast and 2 meters at this heading. So draw and measure the sum. All right, so the thing we do is we draw the first vector. Now that says 3 meters northeast, so you'll see here that yeah, I seem to have used like that's 7.5, so I'm scaling it by a factor of 2.5. And northeast means exactly 45 degrees, and you can see on the protractor that it is. Now, obviously we'll be doing this using trigonometry, so it won't be necessary to have this exactly to scale, but it's helpful to have it roughly to scale because then, of course, it gives you some intuition about what your results should be. Okay, so now, starting at the end of that first vector, I'm just going to do a tiny little coordinate system here, because now we need to draw our second vector, starting right here. Okay, so our second vector is 2 units long, and it's at 30 degrees south of east. So let's get this ruler out of the way here. And so here's our other ruler, and I've already got this set at 30 degrees. So I got to use the same scale, right? So I was scaling it by a factor of 2.5. Just because that makes a nice size diagram. And you see this one is 5 units long on the ruler, which is 2 meters of distance. And so now we've drawn the second vector at the end of the first one, and the sum goes from where we started to where we end up. Now in your notes, you probably don't have a ruler, so you're just going to kind of sketch this one roughly 3 units long, and this one 2 units long, and then this will be your sum. Okay, and obviously we're interested in what that sum is, so we want to know how long it is, and then at what angle it's at. Okay, good. So let's sweep it up and see. So we can see the angle looks like about 17 degrees, and with a scale factor of 2.5, it kind of looks a little bit more than 4 units long. So the sum is about 4, I don't know, maybe 4.1 or something like that meters at about 17 degrees, roughly. Now, you could see this is just a triangle, and we could use triangle trig to get an exact value for that. And we'll talk about that when we meet in class. But all we really want to practice here is just, or all we really want to be introduced to here is just that idea, the algorithm for adding vectors. You draw the first one, at the end of the first one you draw the second one, then you can find your sum or your resultant vector. Now the reason that's interesting, of course, is that in kinematics we're going to want to be adding vectors. So I'm skipping a page or two there in the workbook, but here's another example. So let's say we want to add an initial velocity of 3 meters per second to the east. So there's 3 meters per second to the east. And then we have an acceleration that is for 1.5 meters per second to the south for a time of 4 seconds. So this will be 4 seconds here. So this is 3 units long, and this is 1.5 meters per second squared for 4 seconds. Let me put the units there. Okay, so we've got to take this vector and we've got to multiply it by 4. Well, that's going to increase its length by a factor of 4. So instead of just being 1.5 long, it's now going to be 4 times as long. 1.5 meters per second squared times 4 seconds gives us 6 meters per second. And we're still adding this 3 meter per second length to it. Alright, so how do we add these two vectors? Well, we need to add them in order to find the final velocity. Well, 3 and 6, we know that we just use a diagram. So we draw the first vector, then put the second one at the end of the first one, and then the sum goes from, well, where we started. Let's change colors here. From where we started to where we end up, that will be the final velocity. Right there. And with some simple trig, we're going to be able to find out how many meters per second that is and also what direction it's heading. So the reason that we're practicing adding vectors is to do questions like this in two-dimensional kinematics. Now, in addition to adding vectors, sometimes we're going to have to subtract them. And here's our algorithm there. So if you want to do the vector A subtract the vector B, well, we're going to change that to an addition. We're going to add the vector A to the vector negative B, because we know how to add already, and we know how to do negative. So what does that look like? Well, let's say we have this vector A and this vector B. So we're going to add A to the opposite of B. So this here in green, that's the opposite of this vector B. It's going the other way. So this is A in green, and this is negative B. So how do you add two vectors? Well, you draw the first one. Whoops, not that. Come here, you. You draw the first one, that's A. Then at the end of the first one, you draw the second one. That's negative B. So what do we have here? We've got A and negative B, and this would be the resultant of those two. That is the difference, A minus B. It's A plus negative B is this length right here. Okay, so to subtract two vectors, you add the opposite. And we've learned how to do the opposite, and we've learned how to add previously. So, in class, we will practice some of that, graphical techniques. But of course, we want to be able to do this using trigonometry, because then we can do it exactly. The trigonometry is quite straightforward, and we'll practice that here now. So to do vectors exactly using trigonometry, we're going to need first to be able to take a vector and convert to its components. So that means that we need to be able to say that a vector 5 meters per second at 36.9 degrees, that's entirely the same as 4 going horizontally and 3 going vertically. These are both equivalent ways of representing the vector. Now horizontally, as we've seen, we use a little I hat. Vertically, we use a little j hat. So I hat means x-axis, j hat means y-axis. That's just the notation that we use in physics. So let's look then at some vectors here. So minus 3I, that's going to be in the negative x direction 3 units. And then minus 4j, that's going to be in the negative y direction 4 units. So those are the components there, and they would give you this resultant vector. I plus 4j means 1I plus 4j. Here, I'll use a different color for the resultant. There's that vector. 8I minus 3j. Well, that's 8 steps I. That's way over here. Negative 3j would be down 3 steps here. That's this resultant. And then minus 5j is just straight down 5 units. So drawing those components is quite straightforward, as is the process of changing between these two forms. So we call this polar form, where you give the magnitude and the direction. And we're often interested in what the components are. How much is it vertical? How much is it horizontal? What's the x and the y? So key steps are, first of all, draw the vector that you're given. So this is 20 meters per second at 30 degrees. And you can see, oops, I seem to be a little bit off there. Okay, so let me pull that up a little bit. Again, you know, you guys are just going to be eyeballing this. So 30 degrees towards the north, starting from the west. And this is 20 meters per second. So just draw that roughly the best you can. Now, its components. We ask the question, is this vector partly left or partly right? Clearly, it's partly to the left. That we call the x component. Then we say, is this partly up or partly down? Clearly, it's partly up. We call that the y component. Then we just want to know how much is x and how much is y. Now the process we're about to do, we will do hundreds of times in this course, maybe even 1,000 times. We will use SOHCAHTOA, our trig ratio. The sine of an angle, remember, is the opposite side over the hypotenuse. So the side opposite the 30 degrees is the y. So sine of 30 degrees is y over the hypotenuse, which has a length of 20. Now this can be solved to figure out what y is. Cross multiplying the 20, we get 20 sine 30, which is 10 units. So if you're moving at this speed, at that heading, you're going in the y direction 10 meters per second. For the x is the adjacent side to the angle, so we will use the cosine ratio. The hypotenuse is again 20. Cross multiplying the 20, oh sorry, I should write out cos is adjacent over hypotenuse. And that leads to this assertion here. Okay, so now cross multiplying the 20, it'll be 20 cos 30, which is 17.3, I think. And so now we want to express this in components. It now becomes important that this vector was going to the left. That means it's 17.3 to the left, or negative I direction, and it's 10 in the upwards direction, positive j. Just let me check that 30 cosine times 20, is it 17.3? Yes, it is 17.3. Oh, good, so we've got it. So that's really just right angle triangle trig from grade 9 math, finding these two sides from the hypotenuse and the angle. The other direction is also easy. Let's imagine that we have a vector in rectangular and we want to know what it is in polar form. That means we want to know what is its magnitude, how long is that, hypotenuse, and its direction, what is this angle. So because this is a force vector in newtons, I'm going to call the unknown F. We see it's 5 steps I, 5 newtons horizontally, and 2 newtons in the negative j direction. Clearly, we can use Pythagoras to find the magnitude of the force. So it's 29, 5 squared plus 2 squared. So about 5.4 newtons. And then for the angle, we'll use the tangent ratio. Now, we will ignore the fact that this is a negative, since that's just specifying quadrant. And this is 0.4, so for theta, we will do the arctan, or the inverse tan, of 0.4. So let's see what that is. 0.4, where's the second function? Oh, there it is. Shift arctan, 21.8 degrees. So our force vector becomes 5.4 newtons at 21.8 degrees, and this is towards the south, starting at the east angle. So those are important preliminaries then for what we're going to do in class. We'll do some more practice with the graphical addition of vectors, and then we'll show that we can add vectors graphically very easily using these components.